So what's this hype about NOMA? We got together with a bunch of professional friends across the United Kingdom and conceived the Proceedings of IEEE paper, which is due out in December this year. And really this is just a bit of a taster as to what NOMA entails and how it evolved over the years. So my hope is that this will stimulate your interest in the paper. Casting our minds back for a moment to the first generation of wireless systems, these were typically analog frequency modulated systems, and each user had to have an individual unit at the base station which required individual tuning, and hence it was an expensive process. Then during the early 1980s, the member states of the European Union got together in order to develop the first ever international digital mobile radio system of the world, and they opted after long investigations for time division multiple access, where each user had a time slot. 8 time slots were accommodated on each carrier frequency, and so this way the manufacturing process became much more efficient. After all, they required 8 times less user units at the base stations. The orthogonal multiple access philosophy continued its prevalence even for the 3G standardization, where code division multiple access was opted for, and much of the development was centered around the choice of the specific spreading codes. Orthogonal variable spreading factor codes were used in the 3G systems, which facilitated adaptive transmission, and an adaptive spreading factor was activated depending on the required user bitrate, on the channel quality, etc. So this simple schematic here indicates that when the information signal has a bandwidth of B, and we use, for example, a 16 chip spreading sequence, then the power spectral density is spread by a factor of 16, and so ultimately the signal becomes a bit like the noise. It's a much more wideband signal, and the benefit of this is that the interference becomes more noise-like as well. Interestingly, just to digress for a moment, over the generations, the bandwidth have become wider and wider. GSM had a 200 kilohertz bandwidth, whereas the 3G systems moved up to 5 megahertz, and then in 4G to 20 megahertz, and 5G is likely to be much, much higher. So the signal is indeed becoming more noise-like. But what is clear is that when we transmit the signal over the dispersive wireless channel, then unintentional spreading occurs, and so the orthogonality of the spreading sequences, or even that of the time slots, is eroded, and we end up with non-orthogonal signals impinging at the receiver, which is also potentially contaminated by the multiple access interference. Interestingly, this then led to the concept of spatial division multiple access, where the philosophy was that instead of using an orthogonal spreading sequence convolved with a dispersive impulse response, let's just simply use the impulse responses in order to distinguish the users. And so this way we end up with a huge potential variety of impulse responses, and therefore we are able to support a much larger number of users. So the SDMA philosophy is also already a manifestation of NOMA techniques. But even if we cast our minds back to the early developments in wireless, M sequences, for example, are also non-orthogonal spreading codes, and there's many more M sequences than the number of chips per sequence, whereas in case of orthogonal spreading sequences, the number of users we can support is obviously limited by the number of chips. So let's now really look at the anecdotal historic development of various multiple access schemes, which is portrayed in this simple little roadmap. And I won't linger on each individual aspect of the developments over the past 2-3 decades, but what is interesting to see here that the TDMA, FDMA, and the OVSF CDMA schemes, as well as IDMA, OFDMA, etc., all converged at the NOMA square, which is basically the scenario that we want to look at in this paper. And just to really look at the remaining parts of the past 2-3 decades of technological roadmap, in the top left-hand corner we can see here the various MIMO schemes, which had very different design objectives, because BLAST was aiming for improving the achievable throughput, whereas space-time coding really aimed for achieving a diversity gain. And so there was this diversity versus multiplexing trade-off. But from MIMO square emerges multifunctional antenna array street, and this is very interesting because it allows us to combine the various MIMO benefits on an adaptive basis depending on the near instantaneous channel quality, the user requirements, etc. A very intriguing recent development is constituted by spatial modulation, and the benefit of spatial modulation is that we can flexibly choose the number of radio frequency chains. If we wanted to, we can just use a single radio frequency chain and a number of antennas. So looking at 4G square here, very clearly OFDMA avenue led to 4G square, and much of the world now enjoys the benefit of 4G wireless communications at high rates. But as and when the 5G development started, new developments appeared on the scene, for example in error correction coding, and the polar codes have found also their way into the 5G standards proposals, along with the turbo and LDPC coding schemes. Interestingly, none of the joint coding and modulation schemes so far have influenced the standardization of wireless systems so much, but concatenated coding is a prevalent scheme which benefits from a diversity of advantages of the constituent codes. Down here in the middle we see HatNet square, and a lot of interesting developments are taking place in this arena as well, along with the D2D, device-to-device developments, the Internet of Things, and also there's a lot of work on device versus user-centric systems. Up here we can also see the base station-centric solutions. Very briefly down here there's the uplink downlink decoupling street, which basically aims for ensuring that the macro base station that has much more power is capable of high integrity downlink transmissions, whereas the uplink is typically would be received with the aid of a small base station. So very, very interesting network layer developments as well, all leading up to 5G plays. And this is the area which we will be focusing on. But observe here at the top right-hand corner, Quantum Avenue appearing, which is perhaps an interesting new development in the field that will attract a lot of research in the near future. So looking at the next generation network architecture, just really very briefly down here at the bottom again, we see the small cells appearing and the macro base station transmitting downlink, and the small cell base stations receiving signal from mobiles in the uplink. And then very importantly down in the bottom left hand corner we can see the power domain non-orthogonal multiple access scheme, which is really the main thrust of this paper I'd like you to absorb. So a word or two about the power domain NOMA scheme and its operation. Really, the concept of power domain NOMA can be combined literally with every existing scheme, because it relies on the simple principle that if, for example, two users share the same resource, this could be time slots, frequency slots, or codes, but have different powers, then we can actually separate them, and therefore we can increase the achievable throughput. Indeed, the theoretical justification for using NOMA schemes as opposed to OMA schemes is that their rate region is larger, therefore the achievable throughput is higher. So in very simple terms, for this two-user NOMA scheme, what we could use as the enabling technology is, for example, in the downlink, we can see base stations transmissions, which is at a higher power for the user down here, because ultimately this user is at the cell edge, whereas the user in the vicinity of the cell center can receive signal at a lower power. So the user in the vicinity of the base station could actually first detect the signal destined for the distant user and then remodulate the signal and subtract it from the composite signal. So this way we end up here with the detection of the distant user, and this way we can actually use the user in the vicinity of the base station as a relay station. So the basic principle is relatively simple, and it's centered on the philosophy of successive interference cancellation. If the power of the two users is fairly similar, then parallel interference cancellation is likely to be a better solution. But again, the distinguishing feature in this scenario is that the users have a different power. There's many ways of exploiting the NOMA principle. For example, we could invoke it in a cluster-based system where the users could be divided into a number of clusters depending on their angle of arrival or angle with respect to the base station, and several users could be transmitted on the same resource slot or resource block with the aid of beamforming, or alternatively combined with the successive interference cancellation principle of the previous slide. At the same time, we could also use a simple beamforming based scheme, but if we wanted to separate all the users with the aid of beamforming, then we need a large-scale antenna array or a massive MIMO scheme at the base station, and so in this scenario we also need a high number of radio frequency chains. Just to really finally allude to the large-scale MIMO-based hybrid headnets, I already mentioned that some of the users, for example, in the downlink, could be supported by the macro base station, and these large-scale MIMOs could be multifunctional arrays which would have clumps of beamformers, but at the same time some clumps which are sufficiently far apart from each other could be used for space-time coding, and also for blast type spatial division multiplexing schemes. In the uplink, for example, we could use the Pico base stations because they're much closer to the user, but of course we have to deal with all the associated backhaul and fronthaul issues of cloud radio access networks as well. So my hope is that you would enjoy reading the paper and that you find intellectual stimulation and inspires you to new heights in your research.